Good morning to all of you. This is Dr. Nimish Kumar Srivastava, Assistant Professor in Kumar Engineering College, in the Department of Electronics and Communication Engineering. So in this modules of dealing with the complex topic, in the last class we have discussed about the flip-flop, how we can design, what is flip-flop, and how we can give a name to that two terminals of the flip-flop, and what is the way in which we can give a clock to a SR flip-flop, so that whenever we are getting a truth table by using a NAND as well as by using a NOR, that truth table should be valid for each and every gate, that means a NAND as well as a NOR. So that is the thing that we have discussed in our last class. So before discussing about the another complex topic, that means in which we are going to deal with the counters, first we will discuss about the asynchronous counter, and the next lecture we will deal about the synchronous counters. Now before going to detail about the counter, first of all we should know in our last class we have discussed the truth tables. So briefly we will discuss about the how to draw the characteristic table as well as the how to draw the excitation table of the SR flip-flop. So we will discuss only that basic SR flip-flop, how we can draw the characteristic as well as the excitation table before going into detail about the asynchronous counter. So very quickly let us start that topic of SR flip-flop. So in the SR flip-flop, in order to write the characteristic equation, first of all we have to design, we have to in front of our eyes there should be a truth table, or even if you are not writing the truth table on paper, if you remember that by practicing more and more, then that thing is okay for you. So we can draw the characteristic table by using a truth table, because the concept of both the characteristic and the truth table are the same. It's just the way of representation. There is a different way in which we are representing the characteristic table, but whatever the information that is given by the characteristic table is exactly the same as the truth table. So let us try to draw the characteristic table of the SR flip-flop. So how we are going to draw the characteristic table of a SR flip-flop? Just remember the point that what is sequential circuit? Sequential circuit is a digital circuit whose present output depends upon the present input as well as the past output. So we have to keep this point in our mind before we are dealing with the characteristic table. So let us start the characteristic table. Of SR flip-flop. So we will draw the characteristic table of SR flip-flop. So in order to draw the characteristic table of SR flip-flop, let us quickly revise the your truth table. So that truth table is, we are having S and R, we are having output as Qn plus 1, Qn plus 1 complement. Similarly, for the ease of understanding, you can also write the state. So we'll quickly draw this table, and after that we will jump to the characteristic table. So as this two terminal, there will be a 4 combination 0001, 10 and 11. So in the case of SR flip-flop, as we have discussed in our last class, is that whenever we are not providing the input to a SR flip-flop, that means both the input are 00, in that case your flip-flop is holding the past value. So this state can be given a name which is called as a hold state, which is also denoted by in some book you can see that a memory state, because it is holding its previous state. So when it is holding it, definitely there will be a memory. Without memory you cannot hold something for some instant of a time. So that is why it is also called by a name which is called as memory state. So this 00 is your present output is Qn, and the present complemented output will be Qn complement. So this is Qn complement, and final state will be your hold. Now next case, when we are providing a input to a R, that means we are giving 1 to a reset terminal. So when you are giving 1, so obviously your output will enter into a reset state and your complemented will be 1. So this is called as a reset state. Next thing is, whenever you are providing a input to a set terminal, so by its name it will set the output, means that it will give the it will just put the value 1 at the output. So that is 1, and its complemented value will be 0, and this state is called as a set state. Now the last case, 1 1. So in the case of a flip-flop, we have discussed for the SR flip-flop that the case of 1 1 is treated as an invalid state, because it is in this value that your flip-flop get confused, because at the same time it is we are saying that the flip-flop to enter into a set as well as to enter into a reset state. So whenever your flip-flop get confused, it will show a invalid, or it will show some wrong result. So that is called as an invalid state. So we are denoting it by a don't care, and this is called as a invalid state. So we have quickly revised the your truth table of the SR flip-flop. Now with this concept we will move into detail about how we can write the characteristic table of the SR flip-flop. So previously also I have told you that whenever you are drawing a characteristic table, just keep this point in your mind, that what is a sequential circuit? Sequential circuit whose present output depends upon the present input as well as the past output. So in the case of your SR flip-flop, what are the present input? Definitely it is S and R. And what is the past output? It is Qn. Qn is the past output. So means that by your entire input for the characteristic table will be S, R and Qn, and you will finally draw the output, finally write the output for these three input. So means that if you are having a 3 inputs, so combination will move from 0 to 7. So in this way we can easily draw the characteristic table. So now we are moving into the characteristic table. It is SR and Qn and our final output, present normal output. So we are going to draw the characteristic table between these three combinations. So better thing is, because we have to leave some space for the excitation table also, so we will try to take the minimum space for the characteristic table, so that with the help of this characteristic table we can also draw the excitation table. So this is your characteristic table drawn between inputs and outputs. Three inputs, so combination will move from 0 0. Now for the case of whenever you are providing a 0 0 input to the SR terminals, just recap your truth table in your mind, that whenever both the inputs are 0 0, what was the output? It was Qn. That means your present normal output is holding the past output. So whatever the past value will be, that will be copied at present. So at whichever the combination that you are taking for the inputs, and for those combinations if the S and R both are 0, your you know that with the help of truth table that the output will be holding its past value. So what is the past value for this Qn plus 1? It is 0, and similarly for this combination it is 1. So that means your Qn plus 1 will be 0, and for the 0 0 1 it will be 1. Now the next case, whenever you are providing 0 1 inputs to the flip-flop. So whenever you are providing 0 1, that means S is 0 and R is 1, in that case your flip-flop enters into a reset state. So that means both the output will be 0 0. Next case, for 1 0 combination. So in the case of 1 0, definitely the output will be 1. Now the last case, for 1 1, when both S and R are 1 1. In that case we have discussed in the truth table also, this is treated as an invalid state. So that means for these two output we will draw it, write it the don't care, that is the invalid state. So in this way we can easily draw the characteristic table of a SR flip-flop. Now once we got the characteristic table, now the next point is that we have to write the output equation, or also called by name characteristic equation. So how that characteristic equation can be drawn? It is something which can be drawn by visualizing the output. So if we are just taking the help of a K-map, so our output is Qn plus 1, inputs are S and R Qn. So it will be a 0 1 0 0 0 1 1 0 and 1 1. Similarly, we will write the decimal equivalent 3 4 5 6 and 7. Now after drawing this K map, we have to fill the cells. We have to concentrate on the input combination for which the present output value is 1. So it is 1 for 1 and it is also 1 for 4 and 5, 4 and 5, and we are having don't care for these two combinations. So how we can do the mapping, how we can form a group? So remember that you are going to utilize the don't care condition as 1 only when it is giving you a maximum possible combinations or maximum possible pairing. If it is giving you a quad, so in that way you can utilize that don't care value as 1. Similarly, if by using the don't care value, if you are getting a octet, so in that case also you are going to treat that don't care value as a 1. So here in this case we can see that if we consider this don't care value as 1, in that case we will get a quad. So we will draw the quad. So this is our quad. Similarly, now the remaining things that is left is your 1. So you will combine that 1 with this combination and it will give you a pair. So what is the output expression that we will get? We will get the output expression as Qn plus 1 equals to, for this it will be a S and for this it will be a R bar Qn. So that is your output expression for SR flip-flop from the characteristic table. Now similarly, we have to draw the excitation table. Now how to draw the excitation table is, you have to keep some tricks in your mind that when we require excitation table to design a circuit, how you can design a circuit. Whenever you are designing a circuit, what is the thing that that's keep on encircling in your mind is that you know that this will be the output. So based upon that output, you will try to manipulate the input components so that you can get that output, so that you can get your desired output. So you want some adjustment at the input side, means that you are going to find the inputs based upon your outputs. So that is the trick that you have to remember. In the case of excitation table, we know the output, but we have to design the flip-flop. So for designing, you have to concentrate on the inputs, right? So we will try to find out the inputs from the output combination. So we are having Qn and Qn plus 1 as our output, and we are having SR. We will write all the combinations 0 0 0 1 1 0 and 1 1. Now in this case, in order to draw the excitation table, you have to draw the characteristic table. If you have drawn the characteristic table just adjacent to the your excitation table, so that will be easier for you to write the or to draw the excitation table correctly. So in this way, we are going to start first with the combination for which the output value are different. That means 0 to 1 and 1 to 0. So in this case, we will try to, because what is the output? This is your if you consider it as a present output, so this will be the next output, next state, present state, next state. So that means we have to concentrate on the value 0 to 1. Whenever your value is changing from 0 to 1, so we will concentrate the value when it is 0 to 1. So our output value is from 0 to 1 only for the case of 1 0. So that means for this combination, what is the input value? It is 10. So we will write the value 10 here. Now the next case is for 10. That means your output is changing from 1 to 0. So output is changing from 1 to 0 for this point. So what is the input combination for this output? It is 0, 1. So your output will be 0, 1. Input, sorry, this is SR is input. Now next case, whatever the two combination that we are left with is 0, 0 and 1, 1. So let us quickly move to that concept about how we can write the SR input value for these two combination. So it is 0, 0. Output is changing between 0 and 0. For this also we are having 0, 0. So we have to concentrate on these two values. That means for this one and for this one. So just observe the value of SR terminal. Our value of S terminal is remaining the same. It's just holding the value. That means it is not changing the value from 0 to 0. But in the case of R, it is changing from 0 to 1. That means for S, we will write as 0. But for R, we will write it as don't care. It can be 0 or it can be 1. Next case is about 1, 1 combination. So for 1, 1 combination, this is our 1, 1 combination and this is also 1, 1 combination. So for these two values, we have to concentrate on the input values. So for these two, what the thing that we can observe, R terminal is having the same value, but S terminal is changing its value from 0 to 1. So means that S is don't care and R is, value of R is 0. So in this way, we have to draw the excitation table as well as the characteristic table. So for drawing the characteristic table, just remember the point of sequential circuit. What is sequential circuit? It is a combination of present input as well as the past output. So by that you can just observe the whatever the inputs that we are going to take is the SR and QN, and the output is QN plus 1. Similarly, in order to draw the excitation table, just remember the point. If you want to design a circuit, in order to design the circuit, the first thing that you want to just write it down on the paper, that what is the output that I want. You know the output. Only then you are going to design the circuit. Without knowing the output, you cannot design the circuit. You cannot design some arbitrary circuit. You are just going to land up at the wrong result. It's just a random result. So we have to keep this point in our mind. We know the output, and based on the output, we have to find the inputs. So what are the outputs? Output was Qn and Qn plus 1. So you have to draw the excitation table by keeping Qn and Qn plus 1 on this side, and you have to draw the inputs for that values. So that is the excitation table. Now once we have built the concept of the excitation table, now this next point is about the counters. What is counters? So by hearing this word of a counter, the first thing that that might strike in your mind is counter is used to count something. Count number of clock pulse. It is also used as a frequency divider. Similarly, it can also used as to calculate the range in the radar distance. For that also your counter can be utilized, right? So these are some applications in which we can use a counters. So counters are basically drawn by the help of a flip-flop. There will be a series of flip-flop. It depends upon the what is the mod counter that you are using. Mod, if we are saying that counter is a mod 4. 4 is basically telling you the number of state. If I am saying my counter is mod 6, so that means it is telling me that my counter is having a six different states. If I am saying that my counter is mod 10, means that my counter is having 10 different states. So that is the meaning of a mod and counter. So let us move into detail about the counter. So we have discussed the counter applications. Now let us try to write down some description of the counter. Like your counter is basically divided into two category. First is called as a synchronous counter, another is called as a asynchronous counter. So this thing also can be asked in your exam, like what is synchronous or what is asynchronous counter. Similarly, it can be asked in the form of point of differentiation. Now, in the synchronous counter, the same clock pulse will be applied to all the flip-flop. So that is the first point of differentiation. That means same clock pulse is applied. Same clock pulse is applied to all flip-flop. Whereas in the case of asynchronous counter, different clock pulse is applied. I mean, same clock pulse is not applied. Same clock pulse is not applied to all flip-flops. Right? Now the next point can be about the synchronous. Which one will be the faster? Obviously it will be a synchronous, because same clock pulse is applied, so that means all the flip-flops going to be triggered at the same time. So if something is triggered at the same time, so based upon its input combination, it will react, it will produce the output. So obviously it will consume less amount of a time to produce the output in comparison to the its counterpart, that is a asynchronous counter, which is based upon the different clock pulse. So if something is triggered by a different clock pulse, so they are not triggering at the same time, so definitely they are not going to produce correct output at the same time. So it will require some time to produce the correct output. So that is the thing. Speed, this is faster, and this is slower in comparison to your synchronous. Next thing is, point can be written is, it is your synchronous counter is based upon the next state equation, based on next state equation. Next state values also, we can say that, value or equation. Whereas on this side, it is based upon the toggling operation. It is based upon toggling operation. So these are some point of differences between a synchronous and asynchronous counter. Now once we got the what is the basic point of difference between a synchronous and asynchronous counter, now the next topic is about how we can design these counters. So first thing that we are going to discuss is about the asynchronous counter. How we can design the asynchronous counter, how your synchronous counter look like, what is the flip-flop that we can take into account, and how it is going to react based upon the clock pulse. So let us try to discuss that thing. Asynchronous counter, we will discuss asynchronous counter in this lecture, and we will discuss the synchronous counter in our next lecture. So in the asynchronous counter, as we have discussed that it is having different clock pulse. So in this case, we will consider the in flip-flop as J and K. So we are considering both input as 1. We are having Q2, we are having Q2 complement. Similarly, on this side, we are having J1, K1, Q1, Q1 complement, J0, K0, Q0, and Q0 complement, and this is my negative edge triggering. All flip-flops are negative edge triggered. So in this case, this is clock pulse that is applied. So as it is asynchronous, so in this way the remaining flip-flop going to be connected, and at the final state we are getting the output. Both are 1 1, because we have discussed that your asynchronous counter is based upon the toggling operation. So first thing that we have drawn here is the circuit diagram of the asynchronous counter. Now depending on, this is also called as a ripple counter, ripple counter. So we are at present discussing your ripple counter. So in the ripple counter there are two possibilities, either it could be your down counter or it could be a up counter. So based upon its output operation, we will try to fabricate, we will try to conclude that whether it is a up or a down counter. So we will first concentrate on the timing diagram. After that we will try to discuss some tricks that based upon that tricks we can easily conclude that this counter going to be up or it going to be a down. So we are going to discuss the output. In this case, in order to draw the output, first thing that the one most important point related to a ripple counter is that whenever we are trying to write the output, what is the LSB and what is the MSB? Which output should be treated as LSB and which one as a MSB? So remember the point that the flip-flop at which you are applying the external clock pulse, that will be treated as a LSB. So I am applying my clock pulse on which flip-flop? It is a second flip-flop. Like if I am giving the name 0, right? So if I am applying the second clock pulse to the second flip-flop, so definitely my output is written something like this: Q2, Q1 and Q0. So in this way I will write the output. So now after this, the next thing is that clock pulse. Now we will try to write the output and we will discuss that based upon the output whether it is a up or down counter. So let us assume that when no clock pulse is applied, entire flip-flop is having a 0 value at its output terminal. That means all the flip-flop is in the reset state. Next thing is whenever we are applying a first clock pulse. Now whenever we have applied the first clock pulse, that means we have giving a negative triggering to this flip-flop, and when it is triggered, what is the based upon its triggering, it will going to react on the input combination, that is a 1 1, and for the input 1 1 your JK flip-flop toggle its past value. So if the past value, let's observe the past value was 0. So if it is toggling the past value, its value will change to 1. So we now at present will be having a 1 0 0. Now for this next flip-flop, that means for flip-flop Q1, the clock pulse or the output of the previous state flip-flop going to act as a triggering pulse. So means that your flip-flop 1 going to respond only for a transition from 1 to 0, because it is a negative edge triggered. So that means negative edge triggered is the meaning that whenever we are changing the value from 1 to 0, only in that case your flip-flop 1 going to change its value, because there is a transition from 1 to 0. At present, what is the can flip-flop 1 change its value? No, not at all, because the flip-flop 2 is changing the value from 0 to 1. If your flip-flop 1 was positive edge triggered, in that case your flip-flop 1 will react. But at present we have considered the flip-flop in the negative edge triggering, means that it is going to react for the transition from 1 to 0. So here it is 0 to 1, so your flip-flop not going to react, it will hold its past value was 0, So it will remain in the 0 state, and for the 0 clock and for the flip flop 0 also it will hold its past value. Now when the next clock pulse is applied, what is happening? Again your flip flop 2 will be triggered and it will again toggle its value. So value will change from 1 to 0. Now for this transition from 1 to 0, your flip flop 1 going to react, it will toggle its past value, so its value will change from 0 to 1. And for flip flop 0, the transition is from 0 to 1, but it is supposed to react on the transition from 1 to 0. So that means it will hold its past value. Now next clock pulse is applied. In this case again your flip flop 2 going to toggle, so value changing from 0 to 1. Again your flip flop 1 will hold its past value and the 0 will hold its past value. Now what about when fourth clock pulse is applied? In that case your second flip flop going to toggle its value 1 to 0. Again your flip flop 1 going to react because it is a transition from 1 to 0. So it will change its value from 1 to 0. Now your flip flop 0 going to react as it is seeing a transition from 1 to 0. Your output of flip flop 1 is changing from 1 to 0. So it will change its value as 0 to 1. Now next case for 5, again it will change to 0 to 1. It will not change the value, and similarly your 0 flip flop not going to change the value. Now we will consider 6 clock pulse. Again change the value. It will also change its value, but it will hold its past value because there is a transition from 1 to 0. So from 0 to 1. Now in the case of 7 clock pulse, your flip flop 2 again toggle its value. It will also, because there is a transition from 0 to 1, so it will hold its past value. This will also hold its past value. Now on the application of the 8th clock pulse, let's see what is happening. In this case again flip flop 2 going to toggle the value. It will changes to its from 1 to 0. Now there is a transition from 1 to 0, so that means that the flip flop 1 will also react and it will change it will toggle its value. It will also again changes to its value to 0. Again flip flop 0 is seeing a transition from 1 to 0, so it will also toggle its value, so value changes to 1 to 0. Now we can see that on the application of 8th clock pulse, your flip flop or your counter is returning in its initial state. Initially we have assumed that all the counters or all the flip flop is in the 0 state. So what are the different possible states? So in this we can see that possible states are 0, 1, 2, 3, 4, 5, 6 and 7. So that means range is from 0 to 7. Means that total possible states, total different state is 8. So that means this is your mod 8 counter and mod 8 up counter. So that is the meaning of this counter, mod 8 up counter. So in this way we can get the concept of how asynchronous counter or how asynchronous counter can operate. So in this, just remember that observe the triggering. If we are having a negative edge triggering, so your counter going to react only for the transition from 1 to 0. Now in our next lecture video we will discuss about the next type of a counter, as this is a up counter. So in the next lecture video we will see the down counter as well as the synchronous counter. So thank you all. We will meet in our next lecture video of this complex series.